Great, thank you, Francesco. Thank you to everyone, to all the organizers. It's really a pleasure to be here, and uh, I want to. It's always a privilege to get to talk about this topic because I think it's one of, if not one of the most important, if not the most important topics in theoretical particle physics. And so I'll do my best over these next 5 days to do justice to it. Um, so just to orient you a little bit to me, um, so as Francesco said, I recently took I went on leave from the University of Oregon. I took a position joint between CERN and EPFL. So I got to drive here instead of fly. And it's really been a wonderful experience for me to be living in Europe and to be a part of those great institutions. So I want this to be as interactive as possible. Please interrupt me. We'll have some discussion sessions in the afternoons also, but we have a lot of time. And so I'm going to be happy to go slow and just make this the best it can be for you. So please interrupt, and we can go off on tangents as need be and so on. It is so one of the things that I truly love about this topic is that it's right at the interface between some of the simplest and most profound ideas in fundamental physics and some of the most gory technical aspects of fundamental physics. And so my goal today is to spend some time on some of the more conceptual things, do some we'll start getting into calculations a bit, but really I want to spend quite a bit of time just orienting us so that we're all kind of on the same page with the big picture ideas of what is effective field theory all about. And then as we progress, we'll get into more and more technical calculations. You know, I am assuming that you have some experience, certainly with tree-level quantum field theory, and ideally that you've seen a little bit of loops and dimensional regularization and some renormalization. But I'm going to review all of those tools in the context that we'll use them. And in particular, as we review them, I want to show you a couple of places where things change when you generalize to these effective field theories that have operators beyond dimension 4. Okay, so so we'll get into all of that throughout the week, and then depending on the pace we take, we may get into some examples, and even on the last day, again, if we have time, I might talk to you a little bit about something that's been occupying a big fraction of my research time in the last 3 or 4 years, which is applications of these effective field theory ideas in de Sitter space. Okay, I can't help but advertise. So I wrote up a set of lectures. I had the honor of being asked to lecture at the Tassi Summer School in 2018. And as you probably know, when you lecture at Tassi, they twist your arm into writing something up. And so I basically sat down in December of, I guess it must have been 2018, and I wrote an outline, and I said, oh, I'll finish this in a couple of weeks. And then if you go check, you'll see I kind of lost my mind there for about 6 months putting this together. So I'm quite proud of it, and I think we'll follow a lot of the calculations that are presented in here, and then we'll deviate towards the end. But something just I want to highlight, because when I was doing this, I spent a lot of time studying and reading all of the phenomenal EFT lecture notes that had come before. I wrote myself an annotated bibliography because it was all in my head at the time, what's in what set of notes. So if you look in the end of this, even if you don't find these so useful, maybe, because I tried to, let me say, my goal here was to kind of bridge a gap that I felt was there in the literature between where quantum field theory books end, say Peskin and Schroeder style quantum field theory books, and lectures on effective field theories begin, because mostly these lectures are written by experts, and so as someone who came to this from a beyond the standard model background, who learned a lot of these techniques in my research as a postdoc, I felt like I had a unique perspective to kind of figure out what are the things that you need to learn that you weren't just told from your advisor, or that, frankly, a lot of the people who write these notes invented a lot of these techniques. So basically, that was my goal, was to kind of provide, especially in the first half of this, a lot of the building blocks and the tools that you need to go between your QFT book and the lectures. But if that's something, say, you get out of this week we spend together, or you've already have your head wrapped around, anyway, that you can go there, and it's not 100% comprehensive, but I tried to cover the majority of the notes that are out there. Okay. I would venture to guess that all of you have heard this phrase, effective field theory, okay? And maybe you've even, I gave it this cute title because I really wanted to emphasize the idea of scale separation, okay, and the connection to effective field theory. I guess I want to start by just asking all of you, what does this phrase effective field theory mean to you? What are some keywords that come to mind when I say effective field theory? And yeah, please. Perfect. Higher dimension operators, right? Very good. Any other keywords? Yeah. The Fermi model, perfect. One of the quintessential effective field theories. Yeah. Very good. The impact of higher energies, exactly. And that's a big part of what we'll talk about today, right? Is this idea that when we have some scales that maybe are out of reach of the experiment that we're doing, we can still model the impact of higher energies by including these higher dimension operators, right? Yes, please. Very good. It provides us with a nice parameterization of our ignorance. So one of the nice things about effective field theory is that it essentially encodes all of the possible physical effects we can get at low energies, as long as we know what the degrees of freedom and the symmetries are. Great. Any other thoughts coming to mind? That was a great list already. Yeah, one more, please. Matching, very good. So yeah, so that gets a little bit more into the technical aspects of this, but we'll spend quite a bit of time on that idea of matching, essentially the idea of how to go from a concrete UV model and map its parameters onto the ideas of an effective field theory. Excellent. So many of you have already thought about this or have some experience thinking about these things. Let me tell you why I am so fascinated by the ideas of effective field theory. And to me, the conceptual point here is that basically, when you start your career in physics, maybe for you it was in high school, for me it was in early college, you hear these kinds of things said by people with more experience. So physics is dimensional analysis and Taylor expansions, right? So this is what they say when you're taking those, intro courses in physics. If you were taught them well, somebody was probably shouting at you, include the units, include the units, include the units, and you didn't know why, and you always found it frustrating, at least I did, until at some point you realized that the units encode all of the physics, right? If you just learn the stupid dimensional analysis, then you don't actually have to memorize any of the equations because it's built into the units, right? At some level, the units are the laws of physics. And so the remarkable thing is that, as much as that mattered when you were, say, dropping bowling balls off the Leaning Tower of Pisa, for example, which I went and saw this weekend for the first time. It's amazing, and understanding the implications, right, for the laws of gravity. We can take this so much further in fundamental physics, and when we work in natural units, the dimensional analysis really becomes quintessential to the way we think about the theory. And this idea that came up, one of the phrases that was shouted out was higher dimension operators, right, is if as long as we can come up with a good, useful dimensional analysis that takes into account the relevant physics that we're interested in our case, we're going to be talking about relativistic EFTs, so we'll be talking about C and H bar, right? So then the theory really organizes itself in a simple way and tells the story without really having to do any hard calculations, okay? The other aspect of this is Taylor expansions, right? As physicists, we know there are only a handful of problems that we can solve analytically, and putting aside numerical methods, which of course are very important and interesting, if we want to really understand the consequences of the laws of physics, typically what do? We take an exact solution and then we hit it with a hammer and see what happens, right? So we do perturbation theory. And what effective field theory does is it formalizes that in a beautiful way, okay? So typically, when we do these kinds of experiments where we ping something, right, we see how it evolves given a small perturbation, the tool, of course, that we use to capture those effects is a Taylor expansion. And effective field theory is essentially just a fancy Taylor expansion. And in fact, probably on the third day, we'll see how things go. I want to tell you about the so-called method of regions, which is, in my view, one of the most incredible embodiments of the idea that physics is all just Taylor expansions. And it's a very clever way of taking what are, in principle, very complicated multi-scale integrals and Taylor expanding them using the tools of dimensional regularization and quantum field theory in an absolutely beautiful way in order to see that indeed physics just essentially organizes itself in terms of dimensional analysis and Taylor expansions. Okay? Good. So at some level, I want to claim that when we talk about understanding the laws of physics, okay, we're all here to try to understand what is fundamental physics, what's happening at the most microscopic scales in nature. Sometimes we study the biggest scales in nature to do that, right? We look out in the cosmos. Sometimes we use the world's greatest microscope, the Large Hadron Collider, or variations thereof. But at the end of the day, I think everyone in the room is here. These are lectures on the fundamental interactions after all, right? So we're all here to understand what's happening at the most fundamental scales. And so my claim is, it's a bit of a bold claim, and I'm sure anytime you make these bold claims, somebody would be happy to argue with you. But from my point of view, what does it mean to understand fundamental physics? It means that you understand it in terms of an effective field theory, okay? So the central question here is we want to know what are the degrees of freedom, okay? So what do we need when we're describing an effective field theory? We want to know the degrees of freedom, okay? So especially in quantum mechanics, this is all about quantum mechanical fluctuations, okay? So we're modeling, say, some local quantum field theory, and we want to know what are the fluctuations of those quantum fields, which in relativistic quantum field theory manifest as fundamental particles, right? So we need to know what the degrees of freedom are. Then we need to know what are the symmetries that act on those degrees of freedom. From studying quantum field theory and the standard model, these two ideas, I think, are hopefully quite ingrained in you. You understand, we write down some set of local quantum fields, and then we enforce some set of symmetry transformations. In the case of quantum mechanics, unitary transformations acting on the fields, and that tells us what terms we can write in a Lagrangian, right? Ultimately, to describe the dynamics of that system. The new thing in effective field theory is what I'll call power counting. And here we'll mostly talk about it using some parameter lambda. And the idea is when you have a good effective field theory description, this so-called power counting parameter is small. And that's where the Taylor expansions come in, okay? This power counting parameter gives us a small number that we can do perturbation theory with, okay? Now, in normal quantum field theory, we're very familiar with doing perturbation theory. That's essentially all we know how to do, right? It's certainly what you learn in your course on quantum field theory. But the difference between perturbing in a small coupling parameter, say a dimensionless coupling like the coupling in QED. And a power counting parameter is that a power counting parameter is determined by some kind of kinematics. So lambda is going to be something that goes like some small scale divided by some big scale, okay? And this is the idea of decoupling. So again, we're going to get into this more and more, and with more and more technical language as these lectures go on. But from this big picture point of view, the point is, if I have some large separation between dimensionful quantities, okay, then I can usually, frankly, almost always, organize the predictions of that theory systematically as an expansion in the ratio of those physical scales, okay? Now, little m here could be, say, the energy. So one thing that's important to keep in mind when we're talking about effective field theories is that they're only relevant for some range of, say, kinematics. So it could be that your effective field theory is an expansion in low energy processes. That's going to be the examples we're going to talk about mostly here, are going to be examples where we have a light state with mass little m, a heavy state with mass big M, and then we're going to be doing experiments where the energy scales are of order the small mass, okay, much below the big mass, so we can't make the heavier particle at our experiment. But it could be for more complicated EFTs, say for the soft collinear effective theory, for example, which describes decays of bound states of the strong force rates, heavy mesons, or even the production of jets at the LHC. So in that case, the small parameter has to do with the kinematics of the process. And at some level, you're expanding in, you're imagining you have some light-like direction, some very hard particle, and then you're expanding in small fluctuations, either small energy fluctuations or small angle fluctuations around that direction, okay? So that, again, you'll see manifest in terms of a power counting. It's more complicated, and it is not just some universal scaling of momentum, but in fact has directionality. But nonetheless, all of the tools that we're going to set up and that we're going to talk about, they all hold as long as you can figure out the right way to organize the Taylor expansion, okay? So usually when we talk about effective field theory in our quantum field theory courses, we don't use this more technical phrase of power counting. We just talk about the mass dimension of operators, because those are in one-to-one correspondence when we're just integrating out a heavy particle. But here, because I want to prime you, hopefully, to be able to go out and understand more complicated effective field theories, I'll use this more technical language, and we'll talk about things in terms of lambda, okay? So that gives us something to perturb in. And what we're really doing is we're taking advantage of this idea of decoupling, okay? So if you walk away from these lectures just with a big picture perspective, maybe this is not something you're going to ever do research in. If you remember that this is essentially what underlies effective field theory, and you remember this idea that heavy physics decouples, this idea of decoupling, I'll have done a good job. Okay, so these are going to be the two main things that I want to build some theoretical technology around to really convince you that these are made manifest by EFT. Okay, and so this idea that heavy physics decouples is actually central to our understanding of the fundamental laws of nature. So at some level, this is a consequence of locality. Okay. And we'll see this as we get into the calculations, as we start drawing Feynman diagrams. You can really understand this notion of decoupling and the idea of locality as sort of being one-to-one with each other, okay? But basically, the idea is going to be that as we get deeper and deeper into the regime where the power counting parameter is small, in other words, as we take this heavy mass m to be large or larger, then the heavy physics decouples in a controlled way, okay? So this power counting parameter is going to determine the indirect influence of the heavy physics, okay, as we decouple it. And at tree level, it's almost trivial to see that this happens, okay? The propagator has a heavy mass in it after all, right? And so its influence becomes smaller and smaller as you make the mass bigger and bigger because it scales like 1 over m squared for a scalar. Nonetheless, in loops, this can be quite confusing, okay? Because loops integrate over all momenta, and so you might naively think, and in fact, the founders of our field were very confused about this in the 60s and 70s, okay? You might think that because the loop sees all momentum scales, that it violates decoupling, okay? And that's going to be one of the main points I want to show you is how we can take advantage of this power counting parameter to make decoupling manifest even at loop level, okay? So again, at tree level, it's essentially trivial. It's interesting and it's important. And in fact, mostly, when you're working with effective field theory, especially say if you're interested in beyond the standard model physics, you're probably just working at tree level. Nonetheless, I think it's conceptually very important to understand what happens at loop level. Okay, so that's why we're gonna compute a bunch of loops together. Okay, good. So another aspect, another conceptual aspect of effective field theory that we're going to talk about is this idea of universality. So this is also very deeply baked into the philosophy of effective field theory, okay? And again, as you learned quantum field theory, you were probably introduced to this idea, which is basically we, at low energies, we write all possible operators consistent with the symmetries. Okay, and up to, right, and here's where the EFT comes in, some order in the power counting parameter lambda. So again, in when you're studying, say, renormalizable quantum field theories in 4 dimensions, you would include operators up to mass dimension 4. Okay, mass dimension in this case is tracking the power counting. Okay, so so this idea that we write all possible operators up to some dimension is, and then the number of coefficients tell us the number of experimental observables we need to fix in order to start making predictions. That's this idea of universality. If I just tell you I have 3 different scalar fields, okay, I can say they have 3 different masses, so I can tell which is which in my experiment, all at low energies. I have some set of symmetries acting on those scalar fields. Then I know what the rules of the game are. I just want to write down all local operators up to some dimension, up to some order in the power counting. And that's the universal prediction of this low energy theory. Now, again, because our goal here is ultimately to learn as much as we can about the fundamental laws of nature, we're interested in what's happening even deeper in the ultraviolet, right? We want to zoom in further and further. And here, this idea of universality is both a blessing and a curse, right? It tells us that if we just know what the low energy degrees of freedom are, then we can parameterize everything we need to know in order to make predictions at low energies. And we can learn a lot, right? We can learn that our theory is local. We can test experimentally what the symmetries are at low energies. But there's an infinite number of possible UV completions that could be up at some higher energy scale, okay? And depending on their details, any number of them could give us the same predictions at low energies, where we're talking always thinking in terms of there being some error on both the measurements we can make and the predictions we can make. Okay, so you should always think about your quantum field theory as an effective field theory, where really you're only understanding the theory up to some order in this small parameter. Okay, it's maybe not necessarily manifest when you study your renormalizable theories, okay, but secretly there, you're always assuming that this power counting parameter is smaller than, say, any of your experimental errors in your measurements, okay? Otherwise, you would need to start including more and more of these operators, fixing them by doing more and more experiments so that you can make predictions. Okay, so again, there's this idea that at low energies, there's this universal description that emerges, okay, and at some level, one of the goals in the community is to try to map from what we learn at low energies onto possible UV theories, okay? We're looking for hints at low energies of what the next layer of the onion is, right? What's the next scale in nature that we can hopefully start to probe experimentally? Because at the end of the day, we're here to understand what's happening in this universe, and we need to use experiment to do that. Okay. Good. Any questions or comments so far? I did a lot of just blathering, so. Okay, maybe you're mostly familiar with these ideas, which is great. I just want to get us all again on the same page before we spend a lot of time, doing calculations together. Okay. Okay. There's one last important conceptual aspect of effective field theories that we'll talk about together. So let me touch on that, and then we'll start doing some calculations. So this is the idea that effective field theories allow us to resum logarithms. By the way, if you go and read my TOSI lectures, you'll see. I think with you, I'm gonna talk about resummation, but because at the University of Oregon, one of my colleagues there is Dave Soper, who's a very important a hero in the QCD community. He spent his life resumming logarithms, and when I was working on these lectures and I was asking for his advice and showing him some stuff, he said, "Tim, you're not resumming anything, you're summing it for the first time." And so you'll see for Dave, I wrote the lectures always talking about summing logarithms, not resumming them. But of course, we all just call it resummation. And so anyway, it's funny the things that people stand the high ground on. But anyway, the point is, whether you call it summing or resumming, the point is that effective field theories allow us to reorganize perturbation theory in this way, okay? Again, we're going to talk about this quite a bit. I hope it's something you're a little bit familiar with, but what is unlikely, unless you've worked on effective field theory, is that you've done anything with logarithms other than resum them. And so something that I want to show you in these lectures, something that's really a critical feature of effective field theory, is that it works to fix things beyond just the resummation. Okay, so let me give you the example that I assume that you've seen, which is the running gauge coupling. Okay, so in QED, you can calculate, well, this is even more general, but we can, at one loop, resum this series of logarithms into what we call a running coupling, right? And one of the incredible things in quantum field theory is that we can do a one-loop calculation, and then we can use the fact that our theory is independent of the cutoff that we introduce. Again, some concepts we'll review together, to come up with this absolutely beautiful formula which incorporates effects to all loop order, right? So if we just Taylor expand this, we get something of the following form. So we get an expansion in alpha times log, okay? And the point is that when we're in the regime where our power counting parameter is a good approximation, what often shows up inside these logarithms is the power counting parameter, okay? This is not how it was probably explained to you at the time, but when we look at, because you were studying single scale theories, but when we have theories with multiple scales, and we work in the regime where those scales are well separated, where this power counting parameter becomes small, then we can have logarithms that depend on the power counting parameter, and this logarithm can become larger than the perturbative coupling, and perturbation theory can break down, okay? And so one of the most important practical applications of effective field theory is that it allows us to basically to systematically take these logarithms, pull the dimensionful scales inside of them apart, okay, so that we can restore the convergence of perturbation theory and use these kinds of resummed couplings to connect the physics at very high UV scales to the physics at low energies where we're doing experiments. Okay, so this is really the last, at least in the first, in the more conceptual part of these lectures, where I want to just teach you the tools. This is the last really important concept that we're going to spend quite a bit of time on. Okay, I want to show you how we can use effective field theory and this fancy version of Taylor expansions in order to pull scales apart and get a much more convergent perturbation theory. And the new thing at some level is going to be that we're going to include the finite terms that come from loops that you mostly just threw away in your course. Okay, so in your course, you probably focused just on the divergent contributions from loops so that you could compute this coefficient, this beta function, right? And what I want to show you is that the finite parts of those loops do some heavy lifting themselves, and what their role is and what the connection is to effective field theory. Okay. Just to say a few more words about this idea. You know, what we're going to do when we reorganize perturbation theory is we're thinking about this beta as an expansion in terms of the parameter alpha, okay? So the perturbative parameter in the theory. And you can think of this as the alpha log expansion. So when we compute running couplings, okay, very likely this is all you ever did was compute this first term coming from one loop diagrams, but systematically you can compute higher and higher contributions, okay? Going on beyond one loop is a mess, but it's in principle something you can do. And what this does is it reorganizes perturbation theory. So now you have two axes. On one axis, you're doing an alpha log expansion. On the other axis, you're doing an alpha expansion, okay? And in fact, when we're working in effective field theory, what we are doing essentially is we're introducing a third axis, which is the lambda expansion, the power counting expansion, okay? And so these things are all tied together through the loops and so on, but this is what we're doing is we're sort of making the most of our calculations, okay? When we do resummation, we're taking, you know, we're basically squeezing as much blood as we can from the stone of the one loop calculation, right? And we're trying to organize perturbation theory in the maximally convergent way so that we can get the best possible predictions for experiment, okay? So why logs? Why are logs so important in quantum field theory? Well, it's for a very simple reason, okay? There's just this naive picture that we're, at some level, when we're doing loop integrals, we're just integrating these polynomials in momentum, okay? And essentially, this just gives us power corrections, log corrections, or power suppressed corrections, okay? And so depending on, of course, this is for I'm being quite schematic here, right? This is for positive n, this is for n equals -1, this is for n equals -2 and lower, right? So we get these possibilities coming out. We're going to see all of these different possibilities appearing, at least secretly, okay, when we actually get into calculations. But the point is that it's actually very easy to understand these two examples. They're just polynomials, and at some level they get their contribution is localized at a particular energy scale. Okay, but the logarithms, they get contributions from all energies, right? The logarithm, this is dimensionful, it has inverse powers of dimension, right? But the logarithm is dimensionless. And conceptually, that's telling you that it's getting contributions from all possible scales, okay? So the logarithms and the generalizations of the logarithms, the polylogarithms that show up at higher order, or in more complicated kinematic configurations, those are all manifestations of this idea of getting contributions from all scales. And so and this is the reason that we're so obsessed with logarithms in quantum field theory, okay? And in fact, this schematic picture, right, you might complain that what did I say? I didn't say anything here, really, okay? But in fact, I can point you to proof, so from Slavanov in 1973, there's essentially a proof of this idea. Okay, logarithm here should be in quotes, right? It's logs and polylogs and so on, but log type objects, okay, that appear in the perturbative expansion. So in fact, we know that essentially this is all that comes out from iterative Feynman propagators, from integrating over different loops, okay? And just to, again, make this idea, it's so important, want to give this idea a little bit more weight, that logarithms get contributions from all scales. So y associated with a divergence because the log gets so a typical example, right, better than this just schematic thing, we have some I integral d4L over 2 pi to the 4th, 1 over L squared minus M squared. And then in order to evaluate this, we use the standard tricks, okay? We Wick rotate, so we go to Euclidean space. And we integrate over angles. Okay, and we get 1 over 8 pi squared integral from 0 to some UV cutoff, dl L cubed over L squared plus M squared. And that has the form 1 over 16 pi squared lambda UV squared minus M squared log M squared plus. Sorry. And so then we can take this result and we can Taylor expand to understand this idea that the different contributions localize at different scales. So we expand in M squared first before we integrate, okay? So at order M to the 0, we have 1 over 8 pi squared integral from 0 to lambda UV dl L cubed over L squared, and that's 1 over 16 pi squared lambda UV squared. So we see that we get one contribution, okay, which is localized just at the highest scales in the problem, okay, the UV cutoff, right? Because When you evaluate this integral, the contribution from 0 gives you nothing, okay? Then, at order m squared, we have 1 over 8 pi squared integral. Now I need an IR cutoff. An idea we'll revisit later. Okay, so I do, again, I'm just Taylor expanding the propagator there, right? So this is the leading order in m squared contribution. And now look at what happens, okay? I get something that depends both on the UV scale and the IR scale, okay? So again, this is the idea that I'm getting contributions from the full range of integration. My final result cares about both the high scale and the low scale. And then, let's do one more order. And I get 1 over 16 pi squared, m to the 4th, 1 over lambda I r squared minus 1 over lambda uv squared. Okay? And now, by assumption, lambda uv is much bigger than lambda IR, so this is suppressed, okay, and I'm localized in the IR. So, you know, this is a quintessential loop that you've probably computed a few times already in your life, maybe many. We're going to spend, by the way, quite probably most of a lecture on this loop when we talk about the hierarchy problem together. But you can see this idea, okay, that the loop is getting different contributions, and in fact, right, I'm reproducing the Taylor expansion of this answer. Now I have to introduce this IR scale to see it, okay, and we're going to make this, we're going to formalize this in a lot more detail. But I just, again, want to give you this big picture idea of why we're interested in EFT, why we're talking about scales, and how it's going to manifest in the loop expansion, how we're going to think about Taylor expanding these contributions to the loops and incorporating them systematically using the tools of EFT. Okay. Again, I just want to emphasize that once I started expanding this propagator, in order to make sense of this loop, I had to introduce an IR regulator, okay? And the role that IR regulators play in effective field theory is critical. In fact, maybe a third big picture message that, I'll be sending you in this set of lectures is that typically in a quantum field theory course, you spend the first half learning how to do tree level physics, and the second half learning how to understand some all orders results, but really learning how to do renormalization and how to use the renormalization group, right? And you get obsessed with the UV divergences. The whole thing is a UV divergence obsession. It's all about these stupid 1 over epsilons and the dim reg expansion, right? And then figuring out how to incorporate that into resumming a coupling. And frankly, you see renormalization for the first time and it doesn't make any sense, and you think it's all that it's really all tricks, right? And so what I want to convince you of by the end of this is that renormalization is simply just effective field theory. Okay, so this is another one of my slogans, probably worth even writing, is that, so the idea of decoupling, which really is central to the philosophy of effective field theory, is the reason that renormalization works. And once you understand effective field theory, then renormalization is a trivial consequence, okay? So, so I hope if you still find renormalization conceptually confusing, we're not going to spend too much time doing it in detail, but I hope that by the end of these examples we're going to do, you'll come to understand the idea that renormalization is just effective field theory. And if by the time we're done with the scalar field theory examples this is not clear, please ask, and I'll spend some time sharpening this point, okay? So this is a really important conceptual idea. Okay, renormalization is a consequence of decoupling. It's a consequence of effective field theory. But really, even though you spend almost no time in your course on the infrared of the theories, maybe you had a set of lectures 1 or 2 days on IR divergences, and you saw this very strange thing that they cancel between, say, loop diagrams and tree diagrams with extra emissions, right? And then it's just left at that. And maybe someone said, oh, there's double logs or something, okay? It turns out that all of the action in quantum field theory is in the IR, okay? So this, once you know how to do this, you can automate it. There's really nothing to it, okay? And again, conceptually, once you understand it, really you realize the important thing is effective field theory. But the real meat of quantum field theory, the real predictions, are all in the structure of the infrared, and in particular in the structure of the infrared divergences. So the fact that this lambda IR is showing up in this totally naive calculation is already a sign that something interesting is going on. Okay, we have to be careful about what we do in the IR. After all, the IR is where we make predictions for experiments. Okay, and so the zoo of EFTs, the idea that there are many different EFTs depending on the setting, and they have all of this complicated structure, and they're there to resum logarithms and to do all of this heavy lifting for us. It's all about making the most out of the IR. Okay, trying to make the most precise predictions we can for experiments so we can learn the most about the UV. Okay, but when, you know, as I came to this realization through just research practice, it's almost, you become disillusioned a bit with the books because, okay, they're already 1,000 pages. What are you going to do? But at the end of the day, it's really understanding the structure of the IR divergences that leads to a lifetime of research. Okay, the UV divergences you can learn as a graduate student, and you're sort of done with them. Okay, you understand them, and it's all good. And maybe I'll just, as a preview, I know I've been probably speaking too much. We can do more calculations, but you know, this is an important idea, and what we're going to see is that the role of EFT, one of the modern ways of thinking about what EFT is about, is that it turns IR divergences of the full theory, or the UV theory, into UV divergences of the EFT, and that allows us to use the renormalization group to sum logarithms. Okay? And this is probably the most technical statement I've made so far. Again, we're going to do examples, I hope, to really make this point very sharp for you, okay? But this is the modern way to think about what EFT is doing, okay? Because we want these divergences appear, these logarithms appear in the infrared, okay? And they can become large. If you're in a regime where you have a large separation of physical scales, typically you get logarithms, sometimes even log squared, so-called Sudakov double logs, of that ratio of scales. And when that happens, you need some way to systematically resum them. Unless, again, you're like my colleague Dave Soper, who's one of these QCD geniuses who spent his life resumming logarithms by hand, just by studying properties of iterated Feynman diagrams, looking at all orders results. It's voodoo to me. I don't know how to do that. Okay, I'm not that smart. What I know how to do, at least in principle, is if you hand me a systematic procedure, I can turn the crank, I can run it. Okay, so what EFT does is it takes that voodoo, okay, takes the work of those true heroes of quantum field theory and boils it down to a simple prescription, because it converts the IR divergences they spend their life studying into UV divergences. Once I have UV divergences, now I can just use all the tools of renormalization group evolution to sum the logs, okay? So we're going to be finding that we're going to use the same tools you learned in your course, tracking factors of 1 over epsilon and dimreg, give us RG equations that we can use to sum what are secretly IR divergences. Okay. Okay, so that's a lot. Okay, but that's the those are the main goals of that I want to get to over the course of the week. And like I said, we'll see how long that takes. If we have some time at the end, we'll do maybe some EFT examples of EFTs or some other things. But if we get to all of these ideas, I'll be happy. Okay, this is really my goal. And if you understand these things when you leave here, then I'll have done my job. Okay. Good. So the last thing I want to do, and then we'll take a few minute break to stretch your legs, use the restroom if you need it, is just to highlight the idea that there are a tremendous number of examples of different effective field theories. Okay, and so again, my main goal here is to use the simplest examples that I could come up with to teach you universal properties of effective field theory. But at some level, beyond the things we're going to do here, when you apply these tools to real-world examples, all you're doing is the same types of calculations, just say with Dirac matrices or with more complicated integrals, okay? And so I think it's just really useful to keep in mind that there's a zoo of EFTs, okay? And so I think it's worth spending 5 or so minutes just writing a few of them down to hopefully prime you to pay that much more attention. So maybe the most important for the group here is, of course, the standard model. And thinking about the standard model as an effective field theory is something that's becoming more and more important as we have transitioned into the long-term phase of the LHC, the high luminosity phase, okay, where we're really in a statistics-dominated mode, okay? So we're less in a let's discover new particles mode. Now we're in a let's discover subtle indirect effects of new physics. It's much harder. And thinking about the standard model as an EFT is an extremely useful tool for interpreting the program that's happening at the LHC, okay? So there are other things I think are exciting at the LHC that we could talk about in discussion sessions that have nothing necessarily to do with EFTs. But for these purposes, okay, thinking about the standard model as an EFT and understanding it systematically is something that a huge fraction of the community is spending a lot of time on. And by the way, you might think, oh, the standard model's been around forever, effective field theory's been around forever too, these things are really well understood. Well, I'm here to tell you that they're not. I, for one, have been writing papers just on structural aspects of the standard model and as an effective field theory, and I'm happy to tell you about some of those things in discussion or offline, but this is a big open topic, and there's a lot to do here, and a lot of us spend a lot of our time on this, okay? Good. You might have heard of the chiral Lagrangian, or the Goldstone EFT. This is one of the most important examples conceptually because thinking about the low energy mesons, the pions and kaons and so on as Goldstone bosons, required us to develop a lot of very important theoretical tools, both from understanding how to write Lagrangians in the presence of spontaneous symmetry breaking, okay, and the nonlinear realization. So that underlies all of this, the so-called CCWZ construction, but also in understanding how to compute beyond leading order in perturbation theory and how to make sense of things, okay? There was a long time where it wasn't even clear that this effective field theory made sense beyond tree level, okay? Of course, now we understand that indeed it does in the spirit of the kinds of things we'll talk about here. But this is both a very important example just for understanding the properties of the standard model, but also as a conceptual playground for the ideas of EFT. Another important EFT that we may get into by the end is so-called heavy quark effective theory. this is a complementary description of mesons, okay? So here in the heavy quark theory, what we're doing is we're taking a limit, the power counting parameter in this case, lambda, is lambda QCD divided by the mass of, say, the bottom quark. That's, you know, sort of the best example where heavy quark effective theory is the most effective, right? This is a pretty small number, this ratio, and what is absolutely incredible about this formalism, okay, is that you can show that in this expansion, you basically get contributions to physical observables that factorize, okay? So this effective theory, this is not a concept we'll talk about together, unfortunately. It's very interesting. But this idea of factorization is really important, especially when talking about phenomenology related to QCD. But basically, the point is that you get perturbative cross what Georgi called, or not Georgi actually, who called it the brown muck? Isidori maybe? I forget. But basically, you can show that your matrix elements consist of stuff of a contribution that you can compute using standard tricks from perturbative QFT multiplied by non-perturbative garbage that comes from the strong force, okay? But you can do this in a systematic way. So then, for example, you can start taking ratios of observables, and since these things are simply factorized, all of the unknown brown muck stuff that you can't compute drops out of observables, okay? And you can do this systematically. It's awesome, okay? It's very interesting. And we may just set up the effective field theory because it provides me with an opportunity to show you some interesting tricks. So I'm optimistic that we'll get to that by the end of the lectures, at least. And basically, by the way, heavy quark effective theory is essentially just non-relativistic quantum field theory, okay? You can think about it as you take the mass of the heavy quark to be very large, okay, what you're doing is you're integrating out the antiparticle, okay? And so you just have this static heavy object sitting there with all the QCD brown muck flying around, okay? And that conceptual picture leads to this idea of factorization and allows you to do all kinds of just awesome calculations that you wouldn't be able to do without effective field theory. This is also historically very important because all of the framework that we're going to talk about in this set of lectures were developed in the context of heavy quark effective theory, you know, most famously by Howard Georgi, but by many others. It was really understanding whether or not heavy quark effective theory made any sense that led to the modern version of effective field theory I'm going to teach you about, okay? So more examples. People use, this is kind of related to the standard model EFT, maybe I won't even write it, but you know, people use contact operators as portals at the LHC. Contact operator portals. My guess is a lot of you are thinking about dark sectors, because we all are at some level, and so, you know, one of the ways you can connect between the physics in the dark sector and the standard model is just by writing a local operator with some number of dark sector fields, some number of standard model fields suppressed by a heavy scale, okay? That's EFT, okay? And so this idea of using contact operators as a portal is something that's very important in modern phenomenology, okay? I had a paper come out last week where we use this, okay? It shows up all over the place. Going beyond particle physics, there's a very important, absolutely incredible idea in my opinion, which is the EFT of inflation. Okay, and the idea here, it's very closely related to the chiral Lagrangian, okay? But here, there's a spontaneous symmetry breaking of time translation invariance, okay? And that's for a very physical reason, right? The picture in inflation is you have this field that's slowly rolling down a potential, super flat potential, okay, introduces a clock in the early universe, also as, its vacuum energy drives the exponential expansion of space, but that slow rolling leads to spontaneous symmetry breaking, okay? And you can use, essentially, out of the box, all the tools of the CCWZ construction to write down an EFT. You can think of the inflaton as the Goldstone boson associated with the breaking of time translation, okay? And this is an incredibly powerful tool. It covers a huge range of models of inflation, and it tells you, as with all good EFT, that if you know what the degrees of freedom are in the symmetries, in this case the symmetry breaking pattern, okay, then you can write down a universal description. And indeed, in the EFT of inflation, you get a universal kinetic term, and then you get corrections from primordial non-Gaussianities, and you can power count, so you know at subleading order, where the first interactions appear, that there's only two independent observables you need to make to fix the predictions of the theory, okay? It's awesome and super important, okay? So this is very interesting. There's a related idea, which is something I've been working on with my de Sitter guru, Dan Green, who's the real expert on this. I just bring my lowbrow EFT intuition to this collaboration. But basically the idea here is there's another EFT that emerges when we take the long wavelength limit, which is a very important limit during inflation, for example, right? A part of the picture of inflation is that the quantum fluctuations of the inflaton are stretched out by the de Sitter expansion, and then when they cross the horizon, they become classical and they freeze out. Then they come back, and those are the seeds of structure, right? Hopefully you've heard this story. It's one of the most incredible stories in fundamental physics. And the soft de Sitter effective theory makes that idea of freezing out of the modes, which is very hard to see in perturbation theory, a trivial consequence of power counting, okay? And so just because this is something that I've been working on, in the last lecture we'll probably get into this a bit, and I hope I can convince you of the construction and just show you how it works. It's actually just essentially a version of heavy quark effective theory, okay, just applied in de Sitter space. And again, if we get into this, I'll tell you some other applications. We've been having a lot of fun exploring it. Also in cosmology, you'll hear about the EFT of large-scale structure. Okay, here, this is an effective description of essentially the perturbations of the dark matter fluid that collapses into structures. Okay, you can do a loop expansion here. It's a fascinating field. It's something where there's a lot of open questions. People are working on this a lot. And basically what it lets you do is it lets you compare observables from looking at clusters of galaxies and their properties, statistical properties, to predictions from inflation, okay? So it provides a map from the fundamental properties of what's going on during inflation to the perturbation spectrum that we see in galaxy clusters. And essentially this lets you push your predictions to the smallest possible scales before things become nonlinear in a systematic way, okay? There's, one of the most famous set of lecture notes on EFTs, which I can't recommend more highly, is by Jill Polchinski, and where he presents an EFT of the Fermi surface. That should be a capital F here. Lightning will strike me if I'm not careful. So there's this idea, again, that if you have the right degrees of freedom, right, you can organize an expansion, a systematic EFT expansion, in terms of the excitations on top of the Fermi surface. And in fact, much of hard condensed matter physics is essentially effective field theory. They may not use the same language as us, but one of the things that's so amazing about this set of notes by Polchinski, where he introduces this, at least in the language for particle physicists, is that you can see all of these ideas of symmetries, degrees of freedom, and power counting manifest in this important system for, well, for condensed matter, for the fact that we don't fall through the table. Okay, two more. So just because, again, maybe some of you are even working on these, I think they're worth a few minutes of time. So we have something that in the last, I don't know, maybe it's been 5 years now, but very recently, there's been a lot of progress in understanding EFT for binary inspirals. So here, people are using a lot of the tools that we're going to talk about to write down effective descriptions relevant for LIGO. And so here they're doing systematically, they're computing the post-Newtonian expansion. So they're taking basically GR, expanding it as an effective theory, computing some insane loops. It's incredible what they do if you ever look up a talk or look at some of these papers. But they're able to go to higher and higher order in this so-called post-Newtonian expansion and understand the dynamics of these binary inspirals using all kinds of modern tools in quantum field theory and effective field theory. It's very cool. And last but not least, because it's an entire field all in and of itself, is soft collinear effective theory. Okay, this allows the resummation of Sudakov logs and this is an industry now. Okay, so there are people who spend their entire lives just studying the properties of soft collinear effective theory. So, for example, last week at CERN, one of the heroes of this subject, Martin Benecke, he's visiting, and he was telling me about work he's doing in soft collinear effective theory, looking at higher power corrections, and that it's very confusing, and there's all kinds of interesting physics to be understood there. Okay, so just studying what's been a very well-established effective theory for, I don't know, maybe even 20 years now, beyond the sort of leading power expansion is an active area of research. Okay, so even though this is very well developed in a huge literature, there's still a lot, even at the sort of fundamental conceptual level, to be understood about this. Okay, and there's all kinds of interesting things come up, and most of the applications are to either heavy meson decays or jet physics. But I and others were involved in applying this to dark matter indirect detection, okay, where it's very important for making precise predictions. And again, that's something, if you're curious, we could talk about. Okay. All right. So I think that's, of course, not at all an exhaustive summary, but gives you hopefully the idea that effective field theory shows up everywhere. Okay, it shows up when we talk about the Standard Model, when we talk about QCD, when we talk about physics in the early universe, when we talk about condensed matter, okay, when we talk about LIGO even. And so I claim, and I mean it, that the tools we're going to develop together in the next few days are relevant to any of these applications. Okay, so if you really can wrap your head around the simple models that we're going to study together, these simple scalar models, then it opens the door for you to be able to apply these tools to whatever problems you're interested in. Okay, good. So why don't we take 5 minutes? We'll reconvene at 20 after. Stretch your legs, use the restroom, get some water or coffee, and so. Okay, welcome back. Tomorrow I'll do a better job of giving us a break at the hour. Today I really wanted to get through this intro. Here's the plan. Okay, again, we'll see how many days this takes us. It may take us to the end. But I want to get started in part one. I think we can get a little bit into that. Basically, the idea for what are the rules of the game? How do we build an EFT from the bottom up, just in terms of degrees of freedom, symmetries, power counting? Okay. Then we'll probably spill into tomorrow. We'll spend quite a bit of time on just understanding matching calculations at tree level, how to do matching calculations, how to integrate out a heavy particle, and how to interpret that. And the idea of universality will play a role there. We'll see when we make this connection between the UV and the IR that a lot of information gets washed out, okay? And that leads to this idea of a universal EFT. Then we'll get into matching at loop level, okay? So I hope that you have some experience with the ideas in the top panel. If not, it's okay. We're going to take our time, but hopefully what I'll do is maybe frame it in a slightly more technical language with the idea of going then to these loop level calculations. But that at least you've seen some of those concepts or maybe even done calculations similar. When we get into loop level, we'll spend a couple of days probably going through this. We'll talk about summing logs, okay? And then we'll understand how to do matching at loop level. We'll see how decoupling works at loop level, okay? And then we'll spend quite a bit of time on quadratic divergences in the hierarchy problem. This is a sticking point for me, okay? I think students of your generation are not taught this idea properly. This is a consequence of effective field theory. This is not a problem that's going away. And I think actually the longer it goes on that we don't discover new physics motivated by the hierarchy problem, the more important it is that that young people especially understand how dire the problem is, okay? It's not just some minor thing that you can ignore. Then we'll get into an example where we'll really honestly separate scales inside a logarithm, okay? And finally, I'll show you this idea at the end of this of the method of regions, which is one way of understanding the whole framework in kind of an in terms of Taylor expansions. Okay. So let me also say, with this full program here, okay, which the game I want to play. Okay, as someone, I was raised as a model builder, and the goal of model building is to expose mechanisms. Okay, and so I very much approach this outline from that point of view. Okay, and you'll see what we're going to do is we're going to basically write down a bunch of trivial-ish UV theories with scalar fields. So we ignore all the complications of spin. That plays essentially minimal to no role in effective field theory, other than at the detail level, if you want to get the factors of 2 right, or maybe some selection rules that have to do with spin right. Otherwise, everything can be modeled using scalar fields, and you'll see we're going to write a lot of non-generic Lagrangians, okay? So I'm going to just include the interactions that I need in order to make a point, okay? So this is very much in the spirit of just trying to build the simplest model I can to expose some physics. And you'll see some of these models are a little odd, but then when we draw the diagrams, you'll understand why I made the choices I did, okay? And as always, especially now, you know, in that first part, mostly I was just talking, maybe telling you things you knew, hopefully telling you some new things too. Now we're gonna get into technical details, so, you know, hold me to the factors of 2, make sure you understand what we're doing. Again, I want to emphasize with EFT, the thing that makes this so much fun is that there's all these big conceptual things going on, but then it all has to play out in the factors of 2. And if you don't get the factors of 2 right, nothing works as usual. Okay, so there's going to be some cancellations and stuff that'll happen that'll be really important for understanding this at the nuts and bolts level. Okay. All right, so I have half an hour. So we'll see. I'm going to try to at least get through most of that first point there, and then next time we can get into point 2. Okay. So, how do you build an EFT? Well, I would argue that the first step when thinking about EFT from the bottom up, okay, at low energies, is to pick a process. Okay, we often think about EFTs as being more general, but at the end of the day, the starting point is some observable, okay? I want to describe low energy scattering of particles called phi at a collider experiment, okay? For example, so that tells me I'm going to be doing some expansion in terms of low energies with respect to some scale, okay? And the degrees of freedom are going to be these particles that I can, manipulate at the collider. And so what are the degrees of freedom? Let's say we're going to do phi phi goes to phi phi, okay? So imagine I have some way to manipulate these phi particles, and I can send them at each other. I can do a scattering experiment, and then I can measure what comes out, okay? So what degrees of freedom do we need? Well, obviously, we want to use a local quantum field. Phi of x. Okay, could even give it a hat. And the point here, the local is critical, okay? That is baked into the way we're going to do everything we're going to talk about. And again, this idea of decoupling is going to be is a consequence of locality. And so certainly for the purposes of these lectures, we want to stay in the realm of local quantum field theories, okay? That means I'm going to write a Lagrangian, which is a function of the fields all evaluated at the same space-time point. Fields and their derivatives, okay? Good. So we can ask, what are the symmetries? And so here we're going to enforce a Z2 symmetry. This is a theoretical input. Okay, maybe you have a bunch of different experimental processes and you're interpreting some way, but at the end of the day, you're making this as a hypothesis, okay? So you're saying, experiment told me I have phi particles. I haven't seen any processes with odd numbers of phi particles in them, so I'm going to assume that there's a symmetry of the theory. Maybe it's only an approximate symmetry, but nonetheless, I'm going to use this as a guiding principle to write the Lagrangian, okay? Oh, and of course, I'm also, in this example, going to use Lorentz invariance. Okay, so should have said this one first probably, but you know what this means, of course. It just means that we're going to never have any open indices and so on, okay, Lorentz indices. Step 3 is, what's my power counting? So I'm going to assume that I have light scalar phi with mass m, and I'm going to do my experiments with energy E of order m. Okay? So I am going to assume at this point that there's some heavy scale or large scale, capital lambda, with m much, much less than capital lambda. So I'm going to organize my theory in terms of a power counting little lambda, which is m over capital lambda, which is a small number. Okay? And the claim is my observables are an expansion in lambda and log lambda. Okay, where again, log lambda, I mean in principle at higher loops, polylogs, and so on. Okay. Now, because I'm assuming that Lorentz invariance is a good symmetry at low energies, I want to be a little bit more pedantic about what I mean by this expansion here, okay? Really what I'm doing is I'm assuming that all the four momenta that appear in my observables are proportional to the fundamental scale in the problem, okay? This is the scale that sort of sets the ruler. Okay, again, when we're doing fundamental physics, right, we're always thinking about things in terms of the most fundamental scale, but then because I'm doing EFT, I'm working at low energies, so I want to think about this as an expansion in order lambda in each of the components of the 4 vector, okay? Now, this has a tilde, and that's important. This is of order lambda, okay? So what this is just saying is no component of my 4 vector is ever going to get of order capital lambda. I have a separation of scales, okay? So this is when I say, you know, things like this, right? What I really mean is it's this combined with Lorentz invariance tells me that I should be looking at expansions like this. We may or may not get to an example by the end where this is not true, but if you go and you start reading about other EFTs, you'll see that there's different types of momentum expansions that appear, and this assumption allows you to take a full theory and systematically expand it as an EFT, okay? Again, here it's overkill, but that's okay. And in particular, this says p squared is of order lambda squared, okay? Which is, what that really means is, to get the units right, I need capital lambda as my ruler, and then that's, of course, little m squared, okay? So, starting with this, okay, now we can determine the power counting for the fields. And that's the next critical step in order to be able to organize our perturbation theory, because ultimately we're doing some kind of expansion in terms of local fields, and we want to be able to understand how many operators to keep at a given order in the lambda expansion, okay? So in order to apply our power counting, we use the fact that quantum mechanics is relevant, okay? So here's where the dimensional analysis comes in, okay? Is that we're assuming the commutator between x and p is non-trivial, okay? This is what it means to set h bar equals 1, is that the commutator of x and p matters. If we set h bar to 0, they would commute, and we would be in classical physics, right? But here we're talking about particle excitations, quantum particle excitations, and so this is better be important, okay? So if this is I, which is order 1 in our expansion, then we've determined from our experimental setup what the scaling of p is going to be. So if this commutator is going to be of order I, or order 1, that tells us what the scaling of x needs to be, right? It needs to be the inverse of p. So this immediately tells us that the scaling of x is equal to 1 over the scaling of p, and so the power counting for d4x is lambda to the minus 4, okay? Again, this is exactly the same as mass dimension, right? I'm just using this more formal language because this generalizes easily. Mass dimension doesn't necessarily obviously generalize so easily, but if you always come back to this, okay, in quantum mechanics, then you can figure out what the power counting needs to be for your position space. Oh, I can leave this. Let's go here. All right, so now let's organize, let's start to write down what kind of terms we can find in a Lagrangian. Okay. So the most important thing is to get a kinetic term. So in particular, we want propagation. Well, if we want propagation, we want to be talking about going from one point in space-time to another, okay? So we want some operator that's quadratic in the field. So that tells us we need 2 powers of phi. We also want propagation to be associated with dynamics. Okay? So in order to get dynamics, we need time evolution. And in a relativistic theory, dynamics we need partial derivatives. Okay? And of course, we're going to want them to be Lorentz covariant because we're going to work in a Lorentz invariant setting. And so this is sort of, again, this is a fundamental assumption, right? We're trying to model the dynamics of some propagating scalar field. So we better have some operator with derivatives. And then Lorentz, of course, tells us that it's going to have to come as box because phi is a scalar field, right? It has trivial Lorentz transformation properties. And so the only possible object we have is pairs of derivatives acting on phi, okay? Again, if you work in a Lorentz violating EFT, say the heavy quark EFT, where you're in the non-relativistic limit, this is no longer true, and you can use a different power counting. You can single out the time component, for example, which is what you do in heavy quark effective theory, which allows you to build more general types of operators involving derivatives. Okay, they're not necessarily Lorentz invariant. All right, so that's it. I have 2 powers of phi. I have 2 derivatives. So let's write the most general Lagrangian we can. So we have some factor z1 d mu phi squared plus z2 phi d mu phi plus z3 d mu phi d mu phi. Okay? So those are the 3 unique terms I can write using 2 phis and 2 derivatives. Okay? But notice I have unknown coefficients here, z1, z2, and z3. Okay? And so if first thing I can do is that first term I can simplify, right, just using standard rules in calculus. And so d squared phi squared is simply 2 times phi d squared phi plus d mu phi squared. Okay, so this amounts to a redefinition of z2 and z3. Okay, in other words, I can always shift z2 and z3 to absorb z1. Okay, so z1 can't be physical. So that's how to deal with the first term. Now I have 2 terms left. Any thoughts on how I relate the second and the third term? Integration by parts, exactly, right? So in quantum field theory, I always throw away surface terms. And so I can use integration by parts for free, right, to move derivatives around. And so I'm going to use that trick. I'm going to use the fact that d4x phi d squared phi equals phi d squared phi evaluated at the boundary minus d4x d mu phi squared. So I can absorb into z3. So that gets me to the result we all know and love, which is the form of the kinetic term for a scalar field, which is L equals z phi, I'll call it now, and I'll add this half, which we use for convenience, d mu phi is the unique term. Okay. So now, finally, we have the form of the kinetic term. It's going to give us propagation. We want to use this to determine power counting. Again, we do this the way I hope you're familiar with from your QFT course. So, but from an EFT point of view, the way to think about propagation is that you are doing an infinite number of insertions of the kinetic term. Okay? The idea is we're going to, from the path integral point of view, right, we're going to do a quadratic integral. We're going to invert the kinetic term. We're going to put it in the denominator, right? That's going to give us the propagator. That's one way of thinking about what we do. But when we do that, we do it to all orders, right? There's no perturbative expansion when we do those manipulations. A good effective field theorist is always doing a power expansion anytime they can. And so if this term were power suppressed, then we would only keep the leading interaction. Or we would, said better, we would determine to what accuracy we want to make our prediction, and we would keep that many terms in the expansion. We would insert the propagator that many times if it were power suppressed. So it only makes sense for this particle to yield propagation, or this term in the Lagrangian, said better, to yield propagation if it's not power suppressed, if I can do an infinite number of insertions with no suppression. And so that tells us that, so no power suppression. So our action for this process, integrating the kinetic term, now we know what d4x, how d4x power counts. Okay, it was here, I erased it, but it goes like inverse lambda to the fourth. We want this to be order 1 in our power counting. So the kinetic term goes like lambda squared for the derivatives and lambda phi squared for the field, because there's 2 powers of the field. And so this immediately tells me lambda phi scales like the power counting lambda. Okay, again, this is totally overkill for this simple example, but this is exactly the logic you use in a more complicated effective field theory. Okay. So of course we land at the place you expected, which is that we're organizing this EFT in terms of mass dimension. And a scalar field has canonical mass dimension 1. And so in this language, that's power counting lambda. So now we go to interactions. So the first thing you would write is operators with more fields, right? So what about phi cubed? Can we have that in our theory? No, by what assumption? The symmetry, right? This is forbidden by the Z2. And then that takes us to phi to the fourth, okay? If we wanted, well, let me come back to that. Yeah, so that gets us phi to the fourth, and now, again, we use the same power counting. We determine the dimension of phi to the fourth is lambda to the 4. Okay, so this is what we call a marginal operator, right? This power counts the same as the kinetic term. So, well, let's say no power suppression. Okay. Then, by the same logic, phi to the fifth is forbidden by the Z2. Then we can have phi to the sixth which goes like lambda to the sixth, okay? We can also now start to use derivatives, d squared phi to the fourth. This is again schematic, of course, there's all the ways you can distribute the derivative and so on. This goes like lambda to the sixth. So these appear at the same order in power counting, okay? So if I'm gonna include one of them by just the rules of the game, I need to include both, okay? And then finally, we haven't talked about the mass term yet, and this scales like lambda squared, okay? So we conclude that we can organize these terms using the familiar terminology. Basically, the idea is that in this setup, lambda to the fourth scaling for a Lagrangian term is special. We call that marginal. The mass term scales like little lambda squared, okay? So when we have we call that a relevant parameter. And let's talk about that a little bit. If we write the Lagrangian in terms of the naive scaling here, we would expect to get by dimensional analysis, okay, we would expect that this is proportional to the ruler, okay, the most fundamental scale. But let me put a question mark here. If this were the case, remember, way back, we defined that we're interested in the theory with some power counting little m over big M, or E, maybe better to say E here, right? The energy of our experiment over capital lambda. So if we're probing the theory at low energies and we're in a relativistic theory, if this thing had mass set by capital lambda, this would be way too heavy to generate at my collider. It just would be irrelevant to the physics that I'm doing, okay? So relevant operators are special in that we have to impose, if we allow them to be the size that they would naively be based on the rules of the game, then we wouldn't have a useful effective field theory at all, right? Our starting point would be broken. And so instead of this, we, by assumption, enforce that L is like m squared phi squared, okay? And in terms of power counting, we can think of that now as lambda squared times little lambda squared, and then we get a little lambda squared for phi, okay? Then we can sum this into the propagator, okay? So we're allowed to do this, right? We get to pick the parameters in the theory. But what we're going to find is that this violation of the naive dimensional analysis of the power counting is going to come back to bite us, and that's going to be the hierarchy problem, okay? And we'll talk about that a lot. I don't want to go into it now, but I just want to highlight that there's something weird we have to do, okay? And this is a generic feature of EFTs, okay? Is that they don't necessarily have to explain the smallness of this parameter, but if we don't assume that it's small, then we're sort of not starting from a reasonable point, okay? We're breaking our assumptions going in, okay? Good. So in 5 more minutes, let's just now talk about these terms that go with higher powers, okay? So now when I have lambda to the 6th scaling or higher, now we call these irrelevant. Okay, and at some level, when we talk about scalar field theories in 4 dimensions, right, we often distinguish this as the renormalizable part, this is the non-renormalizable part. But as you may already know, and certainly as I think will become clear by the end of our time together, there's essentially no distinction. Non-renormalizable theories are renormalizable, right? This is just an accident. This terminology is an accident of the history of the subject, where for the longest time, people thought that it wasn't possible to understand these theories systematically because of the UV divergences that appear. And now we understand, as long as you're a good effective field theorist and you power count at every step and you keep track of the power counting, then you're safe. Okay, so that's something I'll talk about a bit as we get into it. But if that's not something you're familiar with, when we get into loops, slow me down. We can go through some of that together. Okay, good. So the last thing I want to say today is just that when we go, so I gave you an argument that the kinetic term was unique, okay? But when we start to get into these irrelevant operators, now we can have terms with lots of derivatives, lots of powers of the fields. There's lots of different structures that can show up, okay? And so it's actually pretty complicated to understand using integration by parts to simplify things, okay, to just like we did for the kinetic term. You do those same manipulations with the higher dimension operators, okay? And there's one other tool we can use to simplify things. Does anybody know what I have in mind? Yeah, good. The equations of motion, okay? But actually, I prefer to say that differently. So the way it's often phrased is using the equations of motion, but what you're actually doing is you're doing a field redefinition. At leading order, you can see that it looks like the equations of motion. But if you want to go to subleading order, you can actually get confused about exactly how to do that. If instead you just try to find a field redefinition that removes derivative terms, okay, and absorbs them into a field redefinition, then you'll see at leading order it looks like you're using the equations of motion, but then at subleading order it gets more complicated, okay? I won't go into this. This is a very interesting idea. We could maybe talk about it in the discussion session. But when we're computing S-matrix elements, it's well known that field redefinitions don't change the S-matrix elements. So we're allowed to do this for our convenience, okay? But ultimately, when you start writing down higher dimension operators, there's a game you play in order to simplify your life as much as possible. That's not just because you want to play with these tools, it's because it tells you how many legitimate free parameters you have, right? If you write down all possible terms, you'll think you have way more free parameters than you do because secretly they're related to each other through these kinds of manipulations, okay? And in fact, counting the number of parameters in an EFT is only a problem that's been sort of systematized and solved recently. And you can understand it using a tool called the Hilbert series, which is something that's been put to great effect in recent years to understand, say, the dimension, the number of independent operators at a given order in power counting for the standard model effective theory and now for many other effective theories. Okay. The last thing I just want to say today, I've been using this terminology without being careful to define it. So let me just define the last thing, which I don't think will surprise you. I'm going to use the idea of the full theory or the fundamental theory and the UV interchangeably, okay? I'm going to use the effective theory and the IR, again, interchangeably, okay? Everything we're going to do together, we're just going to have two levels, okay? We're going to have a full theory with more states in it. We're going to integrate out some of those states to derive an effective theory, okay? But of course, keep in mind that this game proceeds, as soon as we find the next level, the next scale, then, the hunt is on for the scale above that, right? So, today's hypothesis for the full theory becomes tomorrow's EFT and so on, okay? Good. So that's a great place to stop. Next time, we'll talk about tree-level matching and integrating out heavy particles and universality and all that good stuff. So great. Thanks for your attention, and I look forward to the rest of the week. See you later.